Welcome to buffer math. So you've learned about a buffer, what it is. So this is a continuation on that, but now we're looking at the math side because as with most things chemistry, we can also explain it in terms of math. Particularly here, part of it will be finding the pH of our buffers. We can always use a rice table to determine the H3O plus within our buffer and the pH. But there is a more efficient and a better way that we're going to use called the Henderson-Hasselbalch Equation. The Henderson-Hasselbalch Equation works because we're working with weak acids and bases in our buffer. And that amount that they dissociate, that X value, is negligible. So we can assume that X is negligible. Since that approximation is always accurate, the weak acid and the conjugate base will have concentrations that are basically equal to their initial concentrations. So keeping that in mind, we can derive a pH for the buffer solution given the initial concentration of the components that make up that buffer, our acid and its conjugate base. This really just comes from rearranging the acid ionization constant. So if we rearrange the acid ionization constant to solve for our H plus concentration, we get Ka times the concentration of our acid over the concentration of our base. We can rewrite that in terms of the negative log of everything. So we can take the negative log of our H plus value and we get our pH. Negative log of our Ka, we get our pKa, and then we have our negative log of our acid concentration over the base concentration, which will turn it around into the base over acid concentration. Well, within here, Ka is that acid dissociation constant. pKa, again, that P just means the negative log. The concentration of our acid, which is on the bottom in the denominator of that ratio there, is whichever part of our buffer is behaving as the weak acid. It's either the weak acid itself or the salt of our conjugate base. The base in the numerator is whatever is behaving as the weak base in the buffer, so that'll be a weak base itself, or it might be the salt of the conjugate acid. So let's continue and look a little bit more at how to solve these buffer problems. If the buffer is a weak acid, so HA being substituted for whatever anion there, its conjugate salt is a minus. HA is going to be the acid in that case because it itself is a weak acid. A minus is its conjugate base, so that's a base. If our buffer is a weak base, which would be BH plus is the conjugate salt, so B would be the base, accepting a proton to become BH plus, the conjugate acid, that would be our acid. Even if our buffer is using the weak base within our Henderson-Hasselbalch equation, we still need to use our Ka value. We're probably going to have to calculate that using the Kb that is provided. But remember, we know how to do that. It's a formula on our reference sheet. We know that Kw equals Ka times Kb, so we can just simply take our Kw divided by the given Kb to find the Ka that we need for Henderson-Hasselbalch equation. Let's go back and look at these equations again real quick. This here is not on your formula chart. It is simply a rearrangement of our acid ionization constant. But our Henderson-Hasselbalch equation, which is pH equals pKa plus the log of base over acid here, or HH for short, is in fact on our formula chart. So we'll be needing to use that as we go and solve buffer problems. Let's look at our first example here. So we have a buffered solution that contains 0.250 molar ammonia. We're given its Kb and 0.400 molar ammonium chloride. First off, we want to know which species is acting as the acid and which species is acting as the base. Well, let's take out this NH3 first. Well, NH3, that's something that you definitely need to know as a weak base all the time. So NH3, Bronsted-Lowry weak base, must know that. So that means that its conjugate acid would be the NH4+. So that's what's acting as the acid. We also know NH4+ would be acting as the acid because it has that extra proton to donate. NH3 can't donate a proton. It can only accept a proton, which is what bases do. And that NH4+ is coming from the salt part of that buffer. So part B here wants us to show the equilibrium reaction that's happening with this buffer. Whenever we're showing the equilibrium reactions for our buffer, we're always going to take our acid and show the hydrolysis reaction that it is having with water. So our acid is that NH4+, and we're going to react that with our liquid water. When this happens, our NH4+, the acid, is going to donate its proton to form H3O+. And then, since it donated a proton, we'll also have that NH3. So again, in those buffer reactions, we're always taking the acid, reacting it with water to form H3O+ and our base. In this equilibrium system, we have both base and a conjugate acid present, so that conjugate base pair is what's making up our buffer here. If we add a strong base, it's going to react with the NH4+ acid part of the buffer, and if we add a strong acid, it's going to react with the NH3 base part of the buffer. Well, that's not what we're focusing on right now. You should have already learned about that. So let's look at calculating the pH here. We have a couple different options that we can take. Let's look at using that acid ionization constant expression first. If we take a look at that, we have Ka equal the concentration of H3O+ times our NH3 over the NH4+. Well, I know the initial NH3 concentration. I know the initial NH4+ concentration. If I'm looking for pH, I'll need the H3O+, but we also need the Ka. We were only given the Kb, but remember, we just had a little reminder on how we can solve for Ka if we're only given Kb. Because we know that Ka times Kb equals Kw, our Ka will be equal to Kw divided by our Kb. So let's go ahead and solve for that real quick. So that'll give us 5.56 times 10 to the negative 10 for our Ka. And let's go ahead and plug in those other values that we know. So we knew that we had 0.250 molar ammonia initially and 0.400 molar ammonium. So we can plug that in, and then we just have to solve for our H3O+, doing a little algebra here. That'll give us 8.89 times 10 to the negative 10 molar. Once we have H3O+, we can go ahead and find our pH by taking the negative log. When we take the negative log of that H3O+, let's not forget about our sig fig rules. We have 3 sig figs in our number, so we need 3 sig figs after the decimal. Only what's after this decimal is significant in our log values. So that's option number 1 to solve this problem. We're using the Ka acid ionization constant that we should always know how to write, products over reactants, and just plugging in our known values to solve for H3O+. The second option, which I tend to always use when solving a buffer problem rather than the Ka, is using that Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation is again on your reference sheet. It's pH equals pKa plus the log of Ra minus, which would be the base, over Ha, which is the acid. Well, we've already identified what our acid and our base is in part A. So let's just add that in. Other thing we need to know here is our Ka value. Again, we were only given our Kb, so using this as well, we would still have to take our Kb divided by our Kw to get that Ka value. We can go ahead and substitute in all these numbers that we know. So when we do that, our pH is equal to the negative log of our Ka value. That's our pKa is where that negative log is coming from. We had solved for the Ka last time, again, doing Kb divided by Kw to get our 5.56 times 10 to the negative 10. And then it's plus the log of our base concentration, which is the 0.250 molar ammonia, over the acid concentration, which is the 0.400 molar ammonium. From there, we just plug all this into the calculator to find our pH. Again, using these log values, our 3 sig figs will fall after the decimal spot, and we get the same thing as we should. So it's just two different methods to solve this same problem. Again, I generally use this Henderson-Hasselbalch equation anytime that I know I'm working with a buffer to find its pH. So let's go ahead and take a look at our second example here. We're making a buffer solution with a pH of 3.99 by combining our formic acid and sodium formate. Well, we got a weak acid and it's salt. Its salt is that formate polyatomic ion that is right here. We're given the Ka of our formic acid as well. So then, first thing we want to do is write the equilibrium reaction to describe this buffer. We just talked about how to write an equilibrium reaction for buffers on our last example. You can take a look back at that if you need to, but pause the video and try and write this equilibrium reaction out on your own and resume when you're ready to check. So as we said in these equilibrium reactions for our buffer, we are always going to start with our acid. So in this case, our acid part of the buffer is our formic acid. We always take that acid and react it with our water to get our products. Since that formic acid is, in fact, acting as an acid, it's going to donate its proton to water to form H3O plus and the formate conjugate base. So again, we can see our buffer here. We have a weak acid and its conjugate. Our weak acid is going to neutralize any strong base, while our conjugate base there, our salt, is going to neutralize any strong acid that is added. So in this problem, we want to know what ratio of formic acid to sodium formate would be required to make this buffer. Where have we seen that ratio of acid to base? Oh, we've seen that in our Henderson-Hasselbalch equation. Let's take a look at that again. In our Henderson-Hasselbalch equation, we have the ratio of our base to our acid right here. That's what we're going to need to go and solve for. Well, we need to know who our acid and who our base is, if you haven't figured that out already. Our acid, the HA, is the formic acid. Our base would be its conjugate, that formate ion coming from the soluble sodium formate salt. Let's see what else we know. The problem gave us the pH of our buffer, so we could plug that in. It gave us a Ka, so we know how to find the pKa. That's just the negative log of it. We're just going to go and solve for that ratio once we've plugged everything else in. So let's plug it in. So as we plug that in, we have our pH. We have the negative log of the Ka value, which ends up being 3.74, plus the log of our ratio there of base to acid. So we can go ahead and rearrange this, do a little bit of algebra, solve for that ratio. Once we get to this point here, we need to cancel out our log. Well, this is a log base 10, so to cancel it out, we're going to take 10 to the power of both sides. So our ratio then is equal to 10 to the 0.15 power. And we find that it's 1.4. If we go back and read this problem though, it said the ratio of formic acid to sodium formate. Right now this is written as the sodium formate to the formic acid. So let's just go ahead and rearrange that. As written, this ratio means that we have 1.4 moles of our formate from the sodium formate per every 1 mole of our formic acid. So when we rewrite that in the way the problem stated, we're going to have our 1 formic acid per the 1.4 sodium formates. Okay, so that's how we work with our Henderson-Hasselbalch equation. We can use it to find our pH of those buffers or the ratio there. That is all for this buffer video. We got one more part on buffers for the night and continue on to see that.